Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In the last lecture we studied finite element model validation and correlation. In this and the next lecture we are going to study finite element model updating, and this particular lecture is devoted to direct matrix updating method of finite element model updating. So let us first of all look at what is model updating. So in the last class we studied FE model correlation, which involved finding the difference between the FE model predictions and the model test results. And then we also saw that the percentage error in the FE model predictions need to be compared with the acceptable or tolerable error in the predictions, right. And then based on that comparison we decide whether that FE model can be used for the application for which it was made. If the FE model satisfies the criteria of the acceptable correlation with the model test data, then the FE model can be used with confidence for the intended application. But if that error is more than the acceptable level, tolerable level, then what can be done? So other thing we should note that we also discussed that the experimental model analysis results or the model testing results can be considered to be more accurate than the FE model predictions, because model test is conducted on the actual structure and it takes into account all the actual properties of the structure related to the joints, boundary conditions, material properties, right. Everything is taken into account, and that is why the predictions or the results based on the model test are considered to be more accurate. So if the model testing has been done with due precaution, ensuring that there are no errors, then the model test results can be considered to be accurate. So therefore the whatever difference is there, right, of the FE model predictions with the model test result, all that difference must be due to the modeling inaccuracies that might be present in the FE model, right. So whatever modeling inaccuracies are present, that those must be responsible for the difference of the FE model predictions with the model test results. So this observation has led to the development of what is called as FE model updating. So what FE model updating does? The objective of FE model updating is to improve the correlation of the finite element model predictions with the model test results. So that is the objective of FE model updating, and how this is achieved. So FE model updating essentially involves adjusting the chosen parameters of the model or the model matrices to improve the model's correlation with the test data. So different FE model updating methods, they update either some chosen parameters of the model, or some methods even change the mass and stiffness matrices directly, and the objective is to improve the correlation of the FE model predictions with the model test data. So let us try to understand the FE model updating through a flow chart. So FE model updating is done as part of the design cycle of a product or a system, specifically the dynamic design aspect of the product. So let us say for the product or the system an initial design is available. So this is the starting point, the initial design. So based on initial design we make an FE model of the system, right, and in parallel we also construct a prototype of the system, right, based on the initial design. Then we conduct model test on the prototype and then obtain the model test data, okay. We obtain the model parameters of the system, and then those parameters or model parameters are also predicted based on the FE model, and then they are compared with the test data, which is referred as FE model correlation. And if the correlation is not acceptable, then the FE model is updated. So you can see if the correlation is not acceptable, the FE model is updated, and this process is repeated till the correlation becomes acceptable, which gives us a validated or an updated FE model, which will have acceptable level of correlation with the model test data. So this model then can be used with more confidence to predict the dynamic characteristics of the structure and to predict the effects of any structural modifications that might be made as part of the dynamic design. Let us now look at different ways model updating methods can be classified. So the first classification is based on direct and iterative methods. So direct methods are one step procedures, they do not require iteration, right. While the iterative methods, they are iterative in nature, they perform changes in the updating parameters so as to improve the correlation in one step, and then these iterations are repeated till the correlation becomes acceptable. So, this is a most basic classification of model building methods. The other classification can be based on whether the model building method, it utilizes the modal data obtained from model test, or whether it utilizes the FRFs which are measured in the model test. So, some methods are based on model data, measured model data, while some methods are based on measured FRF data. So, other classification can be based on whether the model building method is formulated to update an undamped model of the structure or a damped model of the structure. So, the methods which are formulated to update the undamped model, they only update the mass and stiffness matrices, right, while the methods which address the damped model, they also update the damping matrix of the structure, right, so that the damped response or the model damping factors, right, or the damped FRFs, they are also predicted well by the model. So, these are some ways by which model building methods can be classified. So, now we are going to study in this lecture little more detail about the one of the direct matrix updating methods. So, let us look at what is direct matrix updating. So, direct matrix updating essentially updates the elements of the uncertain matrices in an optimal manner by treating the data assumed to be correct as reference. So, several direct methods were developed when the model building idea was floated, and this started in the aircraft industry, where there was a need to obtain very accurate and reliable validated models for aeroelastic predictions and stability limit speed predictions. So, there are several formulations of direct matrix updating methods depending upon which quantities are updated and which quantities are treated as reference data. So, in this lecture we are going to focus on one of the direct matrix updating method which was proposed by Berman and Nagy. So, we will refer this as Berman and Nagy's method. So, this method essentially updates the mass and stiffness matrices, right, treating the measured model data as reference data, and this is done in two steps. So, in the first step of the method, the mass matrix is updated treating measured eigenvectors as reference data, and this is done subject to the constraints that the measured eigenvectors are orthogonal with respect to the updated mass matrix. So, an objective function J is defined, which is the norm of the product of a weighting matrix W, right, and then the change in the mass matrix delta m multiplied by the weighting matrix. Norm of this product is minimized, and that is called as the objective function J, and this is subject to the requirement that the measured eigenvectors, they are orthogonal with respect to the updated mass matrix. So, here m is the mass matrix of the FE model and delta m is the change in the mass matrix of the FE model. So, m plus delta m is basically the updated mass matrix, and W is the weighting matrix which is given by square root of the FE model mass matrix. So, therefore, this is now a constraint optimization problem where there is a objective function to be minimized and then it is subjected to certain equality constraints. So, this is converted to an unconstrained minimization problem by defining what is called as Lagrangian, which is equal to the sum of the objective function plus Lagrange multipliers multiplied by the different constraints. So, that the unconstrained problem is solved, which basically involves minimization of the Lagrangian, and then that gives us a closed form solution for the unknown updated mass matrix. So, we will not go into details of that derivation, but we will straight away look at what is the solution for the updated mass matrix, and that solution is given by this matrix equation. So, you can see here on the left hand side we have mu, which represents the updated mass matrix, and on the right hand side we have got the mass matrix, which is the mass matrix of the FE model. Then we have the measured eigenvector matrix, which is the eigenvector matrix which will come from the model test, and then we have this matrix m bar, which is given by m bar is equal to phi transpose m phi. So, here again the phi and m are known, so m bar can be computed. So, therefore, from this equation we can now find the updated mass matrix. So, in the second step, the stiffness matrix is updated using the knowledge of the updated mass matrix, subject to the constraint that the measured eigenvalues and eigenvectors along with the updated stiffness matrix and updated mass matrix, they satisfy the eigenvalue problem. So, the optimization problem is defined in this form. So, we define the objective function J, which is equal to half and the norm of the product of the weighting matrix W delta K, which is the change in the stiffness matrix, right, into the weighting matrix W. So, this norm is minimized subject to the constraints that the measured eigenvectors and eigenvalue matrix along with the updated stiffness and mass matrix, they satisfy the eigenvalue problem. So, this is that eigenvalue problem. So, here this is the matrix of measured eigenvalues, right, and this is the measured eigenvector matrix. So, Ku is the updated stiffness matrix, Mu is the updated mass matrix which was obtained at the end of step 1. So, Mu is known here, it is only the Ku which is not known. The other constraints which need to be satisfied are the updated stiffness matrix is symmetric. So, you can see there is a second set of quality constraints which possess symmetricity requirement on the updated stiffness matrix. And then the weighting matrix is the square root of the updated mass matrix. So, this again is a constraint optimization problem because there is an objective function subjected to a set of equality constraints, and this again is converted to unconstrained problem by defining a Lagrangian, which is the sum of the objective function and the Lagrangian multipliers multiplied by the equality constraints, and the minimization of that leads to the updated stiffness matrix. So, let us look at what expression we get after minimization for the updated stiffness matrix. So, this is the expression. So, on the left hand side we have got Ku, which is the updated stiffness matrix, and on the right hand side we have got matrix K, which is the stiffness matrix of the FE model, right, initial FE model, then matrix phi, which is the measured eigenvector matrix, then we have this matrix of measured eigenvalues, and then we also have Mu, which is the updated mass matrix. So, these are the various matrices appearing on the right hand side, and these are all known, and hence we can compute the updated stiffness matrix using this equation. So, let us take an example of updating FE model of a structure using direct method, and here we are going to take the same cantilever structure we have used in our earlier studies at various stages in earlier lectures, and here we are going to perform a simulated study, which means that the experimental data which is to be used for updating, right, will be generated by constructing another FE model of the structure, and that FE model will have some discrepancies with respect to the initial FE model which we want to update. So, we will generate simulated data, experimental data from a simulated experimental structure, and that data will be used for updating a initial FE model of the structure. So, let us look at what is the simulated structure first from which the experimental data is generated. So, this is the, you can see a cantilever beam modeled using beam elements with 2 degrees of freedom at each node, which are translational degree of freedom and 1 rotational degree of freedom. So, there are 10 beam elements, and now this is the experimental model of a cantilever structure. So, in practice what happens, the fixed end of the cantilever may not exactly be ideally fixed, and it may have some flexibility. So, in order to simulate that effect at the clamped end, the torsional spring has been used to represent the flexibility at the clamp end. So, you can see here we have a torsional spring with stiffness Kt, torsional stiffness Kt, that has been used to model the flexibility at the clamped end of the cantilever structure. And this cantilever structure, the length, width and thickness, they are 500 mm, 50 mm, 3 mm, the same cantilever we have used in our earlier studies, and density is taken as 7800 kg per meter cube. The modulus of elasticity for this cantilever is taken as 1.8 into 10 to the power 11 Newton per meter square. So, this value slightly less than the standard value, so which presents kind of a deviation on the metal property of the actual experimental structure. And then we take torsional stiffness as 2500 Newton meter per radian. So, with this data now we construct the FE model of this experimental structure, and then we solve the FE model. We solve the eigenvalue problem based on this FE model, which gives us the eigenvalues and eigenvectors corresponding to the experimental structure. So, once eigenvalue problem has been solved, the first 4 eigenvalues and corresponding eigenvectors, they are treated as the measured eigenvalues and eigenvectors coming from the model test. So, that corresponds to a frequency range of 0 to 400 hertz, the same frequency range we have used in our earlier simulations of the model testing of the structure. Let us now look at the FE model of the structure which we will update. So, this we refer as the initial FE model which has to be updated, and you can see this is the FE model of the cantilever structure. The left end of the cantilever structure is fixed because the experimental structure is supposed to be fixed at the left end, and it has again 10 beam elements, and the dimensions, the density, everything is same for this structure. But the modulus of velocity we take as the standard value, which is 2 into 10 to the power 11 Newton per meter square, because the experimental structure has modulus of velocity which is somewhat different than this. Also, the left end of the cantilever beam, that is the node 1, is completely fixed, right. Both the degrees of freedom at node 1 are completely constrained, and therefore this represents the ideal fixed end. And this is typically what one does in modeling a structure, right. The fixed ends are modeled as ideal fixed ends in the FE model. So, this represents the error in the boundary condition in the FE model. So, there are now you can see there are two errors in the FE model, one is related with the metal property, other is related with the boundary condition. So, now we are going to make use of 4 measured eigenvalues and corresponding eigenvectors for updating. We note that since we have taken measurement at 5 points, we saw on the previous slide that the measurements are taken at alternate nodes, right, at 5 points measurements are taken. So, the measured eigenvector will be of size 5 by 1, while the degree of freedom of the FE model is 22 because there are 11 nodes. So, degree of freedom is 22. So, we see that there is incompatibility between the size of the measured eigenvectors and the size of the FE model. Now, to compute the updated matrices, this inconsistency or incompatibility between the sizes of the eigenvector and FE model matrices, that needs to be resolved, right, and therefore, we expand the measured eigenvectors to the size of the FE model using Syrup method, which we studied in the previous lecture. So, with these considerations, we now update the FE model, and then we compute the updated matrices, the updated mass matrix and updated stiffness matrix. So, this is the comparison of the measured natural frequencies and the natural frequencies and mode shapes in terms of Mach value before and after updating. So, we see that we used the first 4 modes in updating. So, we see that the natural frequencies before updating, they have certain error. For example, the first measured natural frequency was 9.02 hertz, but the natural frequency before updating, that is based on the initial FE model, is 9.61. So, we see that the fourth measured natural frequency is 311.9 hertz and the corresponding frequency based on FE model is 331.42 hertz. So, there is a substantial error. Also, the Mach values based on comparison of the mode shapes, measured mode shapes and the FE model mode shapes, the values are though good, but they are less than 1. And what we see after updating? After updating, the 4 natural frequencies, they are exactly reproduced by the updated FE model, because now they are identical with the measured natural frequencies. Similarly, the Mach values of the mode shapes based on the updated model, they are now 1 for the first 4 modes, which indicates a perfect correlation. So, what we see that the direct matrix updating method has reproduced the measured eigenvalues and eigenvectors that were used in updating. The percentage error is 0, it is completely eliminated. Let us also compare what happens to the 2 modes beyond the updating frequency range, which were not used for updating. So, you can see these 2 measured frequencies 516 and 775 hertz, these frequencies were not used for updating. We see that there is not much improvement in the correlation of these frequencies, because more or less the frequencies have remained unchanged after updating. Similarly, the Mach values have also largely remained unchanged. So, this is the typical characteristics of direct matrix updating method. A direct matrix updating method, it reproduces the data which was used in updating. However, the data which was not used in updating, the modes, the natural frequency and mode shapes of the modes beyond the updating frequency range, not much improvement in their correlation is seen. So, this is not a desirable characteristics of a model updating method. Ideally, we would like that there is some improvement in the correlation of modes which were not used in updating. So, let us also now compare the actual error in the mass and stiffness matrices and the changes which are brought by the updating method in these matrices. And this is possible because this currently we are looking at a simulated study. So, we know the correct mass matrix and correct stiffness matrix. So, this is the comparison of plot of the actual error in the mass matrix with the change in the mass matrix as a result of updating. So, you can see on the left hand side we are plotting the Mx minus Ma. So, Mx is the mass matrix of the experimental structure and Ma is the mass matrix of the initial FE model. So, this difference indicates how much was the error in the initial FE model mass matrix before updating. And we see that actually there was no error in this matrix, because we saw that the discrepancies between the FE model and the experimental model, they were related to the modulus of velocity, which does not affect the mass matrix, and torsion stiffness Kt, which again does not affect the mass matrix, and that is why there was no error actually in the mass matrix. However, updating has caused some change in the mass matrix as shown by the plot on the right hand side, which is a 3D plot of the mu minus ma, which is difference of the updated mass matrix and the initial Fe model mass matrix. So, the difference represents the change in the mass matrix as a result of updating. So, when we compare these two plots, we see that the changes made, they are not consistent with the initial error in the mass matrix. Let us also do a similar comparison for the stiffness matrix. So, you can see here on the left hand side we have got the plot of Kx minus Ka, which shows the difference between the actual stiffness matrix or the experimental model stiffness matrix and the initial Fe model stiffness matrix. So, this plot shows where the error in the stiffness matrix actually existed. So, we see that error exists in entries along the diagonal. On the right hand side we have a plot of Ku minus Ka, which is the change in the stiffness matrix of the Fe model because of updating. And we see that if we compare these two plots, the changes which have been made in the stiffness matrix, they are not consistent with the error in the stiffness matrix before updating. So, this shows that the updating though has reproduced the measured eigenvalues and eigenvectors, the changes which have been made in the mass and stiffness matrix, they are not consistent with the modeling inaccuracies which were there in these matrices. So, ideally we would like that when the correlation is improved, simultaneously there must be a reduction in the modeling inaccuracy in the Fe model, right. So, correlation improvement is achieved by achieving the reduction in the modeling inaccuracies. If that is done, then that model will be improved in a fundamental way and it will make it usable for studying the effect of structural modifications. So, let us now look at what are the advantages and limitations of the direct matrix updating. So, it gives a closed form solution for the updated matrices, because we saw that the updated matrices were in the form of a matrix equation. So, we have to just compute that equation to find updated matrices. So, it is easy to implement and it is computationally inexpensive. So, direct matrix updating is a one step procedure, it is not iterative, right, and so there are no issues of convergence which may be faced in iterative methods. So, direct matrix updating exactly reproduces the measured data used in updating. So, that actually is an advantage because it eliminates the complete error in the Fe model with respect to that data. That is what is the goal of Fe model updating, we are trying to improve the correlation. So, it gives you the best possible correlation for the measured data. However, the limitation is that it may not preserve the connectivity of different DOFs, right. So, we see that the stiffness and mass matrices they are sparse. So, wherever the stiffness and mass elements are 0, which indicates that the corresponding degrees of freedom are not physically connected, right. But when we update the mass and stiffness matrices using the direct matrix updating method, the elements which were 0 before updating, some of them may become non-zero, and which introduces a kind of a connection between those degrees of freedom which actually is not present as per the Fe model discretization. So, therefore, the connectivity information may not be preserved in direct matrix updating. Also, the changes made to the mass and stiffness matrices cannot be interpreted physically. So, it is difficult to associate or attach any interpretation to those changes as to what could be the reasons for those changes in the initial Fe model, what are the reasons for which these changes have been made in the initial Fe model. Physical interpretation cannot be assigned to those changes. Also, because the measured data is incomplete, these methods require that incompleteness issue to be resolved first before updating can be done. So, therefore, either model reduction or mode shape expansion needs to be carried out to implement these direct matrix updating methods. So, these are the advantages and limitations of direct matrix updating. So, in this way we come to the end of this lecture. In this lecture we talked about what is model updating, we classified model updating methods, and we looked at one of the direct matrix updating methods. We also performed updating of an Fe model using direct matrix updating. Thank you.